In November 1930, a German scientist died on the Greenland ice cap, a few days after his 50th birthday, on a supply run to a research station. At the time of his death, his life's idea was considered slightly embarrassing. Geologists had spent nearly 20 years explaining, in print and at conferences, why it was nonsense. The idea was that the continents move. It is now the foundation of the entire science of the Earth. It is taught to children. Every geology department on the planet is built on it. He was right for about 25 years before anyone agreed with him, and he did not live to see any of it. He is one of 4 people in this video who could show their working, and were dismissed for reasons that had nothing to do with the working. Alfred Wegener noticed what schoolchildren notice, that the east coast of South America and the west coast of Africa look like they fit together. Lots of people had noticed that. What Wegener did was go and check whether the rest of the evidence agreed. It did, comprehensively. Identical fossil species, land animals and plants that could not possibly have crossed an ocean, appear on both coastlines and nowhere in between. Rock sequences match across the gap, layer for layer. Mountain ranges end at a coast in one continent and continue in another. Evidence of ancient glaciation shows up in places that are now tropical, arranged in a pattern that makes sense only if those landmasses were once somewhere else together. He put it together into a single claim that all the continents were once joined in one mass, which he called Pangaea, and that they have been drifting apart ever since. The reaction was not mild, it was ridicule. At a major conference in the 1920s, geologist after geologist stood up to attack it. And here is where this has to be fair, because 2 objections were raised, and only one of them was unreasonable. The unreasonable one was about him. Wegener was a meteorologist. He studied weather and balloons and the upper atmosphere. He was not a geologist, and a great deal of the response amounted to a man from another field having opinions about ours. The reasonable one was that he had no mechanism. Continents are enormous. Wegener could not explain what force could possibly push them through solid ocean floor, and the explanations he attempted were weak, and his critics were right about that. Without a mechanism, all his evidence was a set of coincidences that needed explaining rather than a theory. He kept working, kept revising, and went to Greenland repeatedly for his meteorological work. On the 1930 expedition, he made a resupply journey to a station in the interior and died on the way back. The mechanism arrived in the 1950s and 60s, from a direction nobody in that argument had been looking. The ocean floor. Magnetic surveys found symmetrical stripes either side of mid-ocean ridges, recording reversals of the Earth's magnetic field like a tape. New crust was being made at the ridges and spreading outward, carrying the continents with it. Wegener had been right about the what. Somebody else found the how, 30 years after he died on the ice. In 1925, a 25-year-old graduate student at Harvard finished a doctoral thesis on what stars are made of. At the time, the settled answer was that stars are made of roughly the same stuff as the Earth. Iron, silicon, magnesium, the ordinary elements, just extremely hot. That was not a fringe position, it was the consensus. Cecilia Payne took a new piece of physics, the theory describing how atoms behave at extreme temperatures, and applied it to the spectra of starlight, which encode which elements are present. And her answer came out completely different. Stars are overwhelmingly hydrogen, with helium second, and everything else is a rounding error. That is correct. It is one of the most important results in the history of astronomy, and it is the foundation of everything we understand about how stars work. She sent the thesis to Henry Norris Russell, the most senior astronomer in America, for review. He told her the result was clearly impossible. So she added a sentence. In the finished thesis, alongside the correct answer, there is a line saying that the enormous abundances of hydrogen and helium are almost certainly not real. She published it with a disclaimer attached to her own discovery. 4 years later, Russell got to the same conclusion by a different method, and published. He did credit her work, but the finding was attributed to him for a long time afterwards, in the way these things settle. She stayed at Harvard for decades. For years, she was not on the faculty in any formal sense. Her courses were not listed under her name in the catalog. She eventually became the first woman promoted to full professor there through the Faculty of Arts and Sciences, and the first to chair a department. Another astronomer later called her thesis the most brilliant ever written in the field. The objection to it was never the physics. Nobody found an error. The objection was that a student had contradicted everybody, and the student was a young woman, and the most senior man in the discipline said no. Both of those were arguments. Somebody read the work, disagreed with it, and said so wrongly, but out loud, in public, where it could be answered. The next two are quieter than that, and worse. In the next two, nobody argued at all. Gregor Mendel was a monk in a monastery in what is now the Czech Republic, and he had been trained in physics and mathematics before entering the order. Over about 8 years, he grew and crossbred pea plants. Not a few. Tens of thousands, tracked individually, generation after generation, for a specific set of traits: tall or short, smooth or wrinkled, yellow or green. And he counted everything. That is the part that made it work. Nobody else was doing this arithmetically. Breeders had always described inheritance as blending. Mix two things, get something in between. Mendel's numbers said something completely different. Traits didn't blend. They disappeared for a generation and came back intact, in consistent ratios again and again, which meant inheritance was carried by discrete units that stayed whole and got shuffled. He published in 1866 in the Proceedings of a Regional Natural History Society. Now, the legend says he published in an obscure journal nobody read, and that isn't quite fair. That volume went to a decent number of libraries across Europe. The paper was findable, it was just not read, and where it was read, it wasn't understood, because the person reading it needed to already be thinking about inheritance in terms of ratios, and almost nobody was. He sent copies to prominent botanists. The most eminent one he corresponded with encouraged him to switch to a different plant, hawkweed, which reproduces in a way that does not follow the pattern he had found. The results came out confusing, and it went nowhere. Then he was elected abbot, and the job took him. Administration, a long dispute with the government over taxation of the monastery, and the experiment stopped. He died in 1884. His successor is said to have burned a quantity of his papers. In 1900, 3 researchers in 3 countries, working independently on inheritance, each arrived at similar conclusions, went looking through the literature, and found his paper sitting there, 34 years old and complete. He had been right the whole time. There is simply no one in this story to be angry at. It was read by too few people, too early, and then it waited. Lise Meitner was a physicist in Berlin, and for around 30 years she and the chemist Otto Hahn worked together. She on the physics, he on the chemistry, in one of the most productive partnerships in the field. In 1938 that ended, because Meitner was Jewish and Germany was no longer a place she could stay. She left in July with a couple of suitcases and no position, and ended up in Sweden, isolated, in a lab where she had almost no resources and did not speak the language. Meanwhile, in Berlin, Hahn kept running their experiments, bombarding uranium with neutrons, and got a result he could not explain. His chemistry was saying that there was barium in the sample afterwards. Barium is about half the size of uranium. Nothing in physics at the time allowed a heavy nucleus to come apart like that. He wrote to Meitner, because after 30 years she was still the person he asked. She got the letter over Christmas, while her nephew Otto Frisch, also a physicist, also a refugee, was visiting. They went for a walk in the snow and worked it through. The drop-like behavior of the nucleus, the energy released, the arithmetic of the mass that goes missing and where it goes. They came back with the explanation: the nucleus was splitting. Frisch borrowed a word from biology and called it fission. Hahn published the chemistry in Germany without her name on it. And this is where the story gets more complicated than the version that usually gets told. Putting a Jewish refugee's name on a paper published in Nazi Germany in 1939 would have been dangerous for her and for him. There is a real argument that leaving it off was the only survivable option at that moment. But it did not stop there. In the years afterwards, as the discovery became one of the most consequential in history, Hahn repeatedly described it as a purely chemical achievement and pushed her contribution to the edges, and kept doing that long after the war ended and the danger was gone. The Nobel Prize for the discovery of fission went to Otto Hahn alone in 1944. Meitner was nominated many times across both physics and chemistry and never received it. She has an element named after her, Meitnerium number 109, which is a rare honor and is not the same thing. Look at what the actual objection was in each case. Wegener was the wrong kind of scientist, a weatherman with opinions about rocks. Payne was a student, and a woman, contradicting the most senior man in her field. Mendel was a monk counting peas in a place nobody was watching. Meitner's name was dangerous to print, and then inconvenient to add back. Not one of those is a scientific argument. The closest thing to a real objection in the whole video is Wegener's missing mechanism, and even that was used to dismiss a mountain of evidence, rather than to go looking for the answer. Now the uncomfortable part, because a video like this usually stops one line too early. It would be easy to finish here with something about geniuses being ahead of their time and institutions always being wrong. That's the satisfying ending, and it's a bad one, because for every Wegener, there are a very large number of people who were also dismissed, also convinced, also had a theory, and were simply wrong. The filter that failed these four is the same filter that correctly rejects an enormous amount of nonsense every year, and it is not optional. You cannot run a science without it. So the lesson isn't that the outsider is always right, it's narrower and more useful than that. In all four of these, the objection was about the person and not the evidence. And the moment an argument shifts from what was found to who found it, that's the thing worth noticing. None of these four were ahead of their time. They were on time. Everybody else was late. If you want more of these, the strange, hard, mostly forgotten corners of history, subscribing is how you get them. It genuinely helps, and it's free. And if you want the other version of this, a man who was believed and whose discovery still sat unused for 10 years, that one's on the screen now.